Good evening, teachers, parents, and all the wonderful students. Welcome to Pusat Tuisyen Academy YouTuber. Bermula percuma, selamanya percuma. How are you doing today? I hope all of you are ready for today's lesson. Before we proceed, let's begin our session by reciting a prayer for Muslims. The non-Muslims may pray according to your own religions. Okay, let me introduce myself. I'm Teacher Lau from SMK Tinggi Krang, the moderator of the day. We at Pusat Tuisyen Academy YouTuber will provide you with free online classes. Let's take this opportunity to do your revision. So are you ready? Let me introduce our teacher for today's lesson. We have Cikgu Shahnon from College Matrikulasi Pulau Pinang. We are now live on Cikgu Shahnon channel. Please support his channel by clicking subscribe now. The topic of today's lesson is physical properties. And together with us, we also have Teacher Kong from College Matrikulasi Perak, who is control host, in charge ensure the smoothness of our lesson on technical support. And Teacher Tang from College Matrikulasi Selangor as observer to ensure the smoothness of our lesson. So before we begin, I have a few reminders to all of you. First, please pay attention to our lesson and use the chat session wisely. Next, regarding the certificate link, the link will be given at the end of our session. You can use a MOE or the Lima account when you fill in your particulars, and make sure to listen to the passcode given by me during the lesson, and fill in the form within the time limit, which is 30 minutes. So now I will give you the first three passcodes. There's A25. A25. So without further ado, let's welcome Cikgu Shahnon. Okay, Cikgu Shahnon.
Assalamualaikum warahmatullahi wabarakatuh, and very good afternoon. Okay. Before we start, as usual, this is my poster, and this is my profile. My name is Shahnon Benawi from College Matrikulasi Pulau Pinang. Teaching experience about 22 years old, 22 years, and position Ketua Panitia Kimia Prayu in Academy YouTuber. Okay, my channel is www.youtube.com/Shahnon channel, and this is our poster of Kimia Prayu. We have a teacher Vivi Lau, teacher Tang, me, Cikgu Mawar, and teacher Kong. And here is a mathematics Prayu, led by teacher Im. And then here is biology Prayu, led by Cikgu Faizah. And perakaunan and economy Prayu, led by Madam Fizi. And here is physics, led by Madam Rosmaya. Okay, and this one is portal Academy YouTuber Malaysia. Okay, many information we can get from here. And the last one is Aplikasi Academy YouTuber. All right, the biggest what we call it videos video education, more than 20,000 videos PDPC Okay, and without much ado, let's go to our lesson today. Our lesson today is revision about physical chemistry. Actually, this is meant for matriculation student because they will have their examination in this coming Wednesday. All right. Okay. First, we look at the topic is reaction kinetic, and the question number one is define activation energy, and question 1B, the rate constant for the forward reaction between hydrogen gas and iodine. Okay, we go to the definition first. To answer this question, of course, student should remember, okay, the definition of activation energy. This is very, very important. And activation energy, we can use EA. EA is the definition is the minimum kinetic energy required. All right, EA is the minimum energy required by reactant for effective collision. For effective collision, in order to start the reaction. Start the reaction. Okay, this is definition. You have to know it, and usually for definition the marks only 1 mark. Okay, this is the things that you have to put in your definition. Minimum energy required, okay, by return for effective collision in order to start reaction. Okay, this is definition of activation energy. Now we go to the B. Okay, this one is A. Okay, let me put it. Okay, the rate constant for the forward reaction between hydrogen gas and iodine gas is 138 liter per mole per second. The activation energy for the reaction is 165 kilojoule per mole at 700 degrees Celsius. And we are given the equation here. Okay, the equation is given. So easy for us. All right. Delta H is negative 9.48 kilojoule per mole. Sketch and label the energy profile diagram for this reaction. Okay, we have to sketch. Number one is you have to sketch the x and y axis. All right, x and y axis. The y axis we have to label. Actually, y is potential energy. This one is potential energy, and x axis is reaction pathway. This one is reaction pathway. All right, and then the most important here is delta H here. If you look at the delta H, the value of delta H is negative. That means this is exothermic. You have to know the shape of exothermic. For exothermic reaction, the shape is like this. Like this. All right. Okay. The value of product, here is a product, must be less than the value of reactant. Okay. And then, of course, we have to label the reactant. Reactant is here, hydrogen gas plus iodine gas. Okay, you have to label this, and also label the product. The product is 2Hi gas. Okay, for axis and you write the potential energy and reaction pathway, maybe you will get 1 mark. And for the shape like this, maybe another marks for that. And then here we have a delta H, and also we have here, let me sketch for you, deactivation energy. Deactivation energy is 165. This one actually is for the forward reaction. Forward reaction means from reactant to this peak of what we call it, graph. Okay, if we call it graph. Okay, here is EA. This is EA forward. Okay, EAF. F stands for forward. Is a negative 165. Okay, 165 kilojoule per mole. Okay, 165. Okay, minimum energy required. This is the minimum energy required for the reaction to occur. 165 kilojoule. And then we also have a negative 9. Negative 9 actually is the different between product and reactant. Here is delta H, negative 9.48 kilojoule. Okay, now we already finished a sketch and label the energy profile diagram for this reaction. Okay, now we have settled question 1B. We go to the C, question C. Determine the activation energy and rate constant for the reverse. Okay, the question is activation energy for the reverse reaction. This one is 165 is activation energy for the forward direction. Now we have to calculate, we have to determine the activation energy of reverse. And then also we have to rate constant here. Okay, we have a rate constant here for the reverse, because here we already know the rate constant for the, this one is rate constant for the forward reaction 138 liter per mole per second. Okay, we already know the rate constant for the forward. Now we have to calculate the rate constant for the reverse. Assume that Arrhenius factor A is the same for both reaction, right? Okay, first we have to determine the activation energy for reverse, and this one actually not difficult, because EA for reverse from this one is product. Okay, product to the peak of this graph. Okay, from here to here. Okay, this one, like what I sketch here, is a EA for reverse. If you look at this, we know that we just add 165 here and plus 9.48. Okay, 165 plus 9.58 is activation energy for reverse, and the value of EA always positive because energy needed. All right, here if you look at here, this is negative 9. Just forget about the negative sign. We just take the 9.84. So the answer is 174.84 kilojoule per mole. Okay, now we already answered the activation energy for the reverse. And then the second one is to calculate or to determine the K, all right, because this one is rate constant, or rate constant for the reverse. This one we need to use what we call Arrhenius equation. Okay, let me use this one. So to answer this question, first you have to remember the Arrhenius equation ln kf. Okay, this one is for forward, because all the data for forward we already know. Ln kf equal to ln a negative EAF over RT. Okay, this one is Arrhenius equation, and I put the K for F. F stand for forward, because we already know the value for forward. Okay, so this one I want to calculate the A. Okay, ln A here. So this one become ln KF plus EA over RT, because in this question it is given that the Arrhenius factor is the same for both forward and reverse. So if I can calculate the A value for forward, that one also A value for reverse. All right. And then K for forward is 138. Okay, ln 138. Okay, here, look at here, this one, 138. Okay, 138. And then we have uh, the temperature is 700. We have to change to Kelvin. Okay, KF138 EA. Okay, EA also we already know. EA is 165. For this one, 165 we have to change to joule. Okay, so times exponent 3. Okay, we have to change to joule. Divided by R is 8.314, and the T 700 plus 273 become 973. Okay, 973, and then the value of ln A is 20 if you use our calculator, and this is the answer. Okay, this one. All right. Okay, when we finish this one, okay, then we can calculate the ln K for reverse R. I use R here, and then ln A. Ln A we already calculate here, and then minus EA for reverse over RT, right? The ln A is this one, 25, 3, 500, Okay, ER, we already calculate 174, right? 174. Okay, this one is 17484, this one, this one. Don't forget to change it to joule, exponent 3 divided by 8.314, and same temperature 973. Okay, and lastly we can calculate the value of K, and the answer is 40.889. And don't forget to write the let me write the unit, and the unit must be same as K forward. Okay, liter per mole per second. Liter per mole per second. Okay, liter per mole per second, or you can use per molar per second also can. Okay. Okay, this is answer for question number 1. Any question from the floor for this question? Any? Or no? No question? Okay. I think no question. So I can continue. Okay, let me continue. Question number 2. Question number 2, still reaction kinetic. Given rate equal to K, concentration of NO2 squared Cl2, by what factor does the rate increase if each of the following changes occur? We triple the concentration of NO2, and the second one is we just double the concentration of NO2 and Cl2. Okay, to answer this question, I think this is quite easy. Okay, first we just write the rate law here. The rate equal to KNO2 squared Cl2. For number 1, we just triple NO2. So NO2 here we triple. So it will become K3 here, NO2 squared Cl2. And the 3 here, 3 to the power of 2 becomes 9. So it's become 9K NO2 squared Cl2. So from here, we know that the rate will increase by a factor of 9 or 9 times 9 times. It will increase 9 times. Okay, the rates. And then the number 2 here, we just increase, we double the NO2, and also we double the Cl2. So the equation will be like this. 2 to the power of 2 is 4. 4 times 2 become 8. So here become 8K NO2 squared Cl2. So 8 times. Okay. When we double NO2 and we double chlorine, what happened? The rate will increase by a factor of 8. Okay. Okay, B. Question B. Compound X decomposes according to the equation X equal to product. It was found that 50% of X had decomposed after 100 minutes. How much of X will remain? Okay, after 150 minutes if the reaction is first order. The most important thing is here is first order, and then here we have a 50%. Okay, first order. That's mean the 50% decompose 50%. That's mean here we have what we call a half life. Okay, this is actually is half life of this compound X. So we can use half life equation for first order of reaction. That is T half equal to, this one is C. Oops. T half. This one is what? Let me see first. Okay, B. T half equal to ln 2 per K. Ln 2 per K. Okay. This one is half-life of first order. Okay. You have to remember the half-life of the equation for half-life for first order. Okay. 50%. And then decompose after 100 minutes. That's mean the T half is 100 minutes. This one. This one is 100 minutes. And this one is ln 2. And then here is K. That's mean we can calculate the K. Okay. The K. And we just use your calculator, and the answer is 6.93 exponent -3 per minute. Okay, why per minute? Per minute because this is first order. Per time. Okay, the unit for constant for first order is per time. If second, that will be per second. For minute, per minute, per hour, like that. And then when we know the K, now we can calculate how much X will remain after 150 minute. Okay. And then we will use the equation of this one, ln X, ln, usually we use this one, right? Ln A naught over ln AT equal to KT, right? Okay, we use this one. For this one is X, we just change it to X. Okay. And the beauty of first order is whatever it is, we can use the initial concentration of the initial concentration or the A naught, we can always use 100%. No problem for first order. For zero order and second order, we cannot. We have to change to the original concentration. But for first order, okay, this is easy for us. Okay, because we just can use this as 100%. Okay, and then we want to know the xt here, and k 693 exponent -3. Okay, this one is per minute, so we just add 105 150 a minute here. So when we calculate it, the answer is xt is 35.4%. Okay, this is the answer for this question. Decompose, had decomposed. Okay, that's mean after 150 minutes, the compound X become remaining. The remaining is 35.4% from 100%. Okay, from 100% after 150 seconds. After after 150 minutes, it's become 35.4% of its concentration from. Okay, there is for reaction kinetic. Excuse me. Now, okay, we go to the thermochemistry. Okay, now the question for thermochemistry. The question is define the enthalpy of combustion. Okay, okay. The answer is heat release. Okay, remember that when the combustion, the heat release, because when we burn something, of course, it will release heat. Okay, heat release when 1 mole of substance is burned completely in excess oxygen at a standard condition. And standard condition for thermochemistry is 25 degrees Celsius and 180 M. Okay. B. A bomb calorimetric experiment is performed with powdered xylose C5H10O5 as the combustible substance. The data obtained are using 1.183 gram and heat capacity of calorimeter 4.7 to 8 kilojoule per degree Celsius, and initial calorimeter temperature before combustion 3.29 degrees Celsius, and final calorimeter temperature, that's mean after combustion, and it will raise the temperature of calorimeter to 7.19 degrees Celsius. Okay, that's the data. And then the question is calculate the heat of combustion of xylose in kilojoule per mole. Excuse me. Okay, we have to calculate the heat of combustion. Remember that the heat of combustion means, according to this definition, the heat released when 1 mole of substance is burned completely. But in this all right, but here we given only 1.183 gram, and I believe this is not 1 mole, so we have to calculate. First of all, we are given mass, of course we have to calculate the mole of, this one is B1, we have to mole of xylose. Okay, we have to calculate mole of xylose first, and I think all of you know how to calculate it. Mass over molar mass. Okay, 1.183 gram divided by the xylose is here C5H10O5, so 12 times 5 plus 10 plus 16 times 5, right? Okay, use your calculator, and the answer is 0.00788 mole. Okay, actually we just burn 0.078 mole of xylose. Okay, and then with this data we already know that, and when we want to use we want to calculate the heat capacity or whatever, we will use this one, heat release in this case is released by combustion, equal to heat absorbed by surrounding. And heat release here from combustion, okay, we will use Q here. And heat absorbed, if you look at here, we only has the data of a calorimeter. Okay, even though we know that in bomb calorimeter, usually we have a water inside the bomb calorimeter. But this one, we are not given any, let's say, mass of water or whatever. So we just use C here and delta T. The capital C here is actually is heat capacity of calorimeter. Okay, 4.728. Look at the unit, kilojoule per degree Celsius. Okay, this is very, very important. And then the delta is 7.19 minus 3.29. So the answer is 18.4392 kilojoule. Okay, kilojoule, because I state the kilojoule there. I not change it to joule or whatsoever. So just put it as a kilojoule, easy for us to calculate later on. Okay, this one, 18.4392 kilojoule here actually come from when we burn 0.08 mole of xylose. So we can calculate the 1 mole, right? 0.0788 mole xylose will release, okay, it will release, this one is a release, 18.4392 kilojoule. If 1 mole, okay, xylose, okay, it's become 18.4392 divided by 0.0788 mole. So the answer is 234 kg. All right. Okay. So after that, we can make it more proper. So we can use this one, delta H not C. C meant for combustion. For xylose, C5 H10O5 equal to negative. This one we have to put negative because this will release heat, 2340 kilojoule per mole. Okay, this is our final answer for this question. Okay, because calculate the heat of combustion of xylose in kilojoule per mole. So this is the answer for this question. Delta H C naught xylose equal to negative 2340 kilojoule per mole. All right.
Shahnon,
And then,
can you state for advertisement?
Okay, advertisement. All right.
Okay, thank you.
Yeah, teacher Lau, can I proceed?
Sorry,
Or you have?
I forgot to open my
Okay.
mic. So before we begin, I give
Yeah.
you the second pass code 9797. Okay, teacher Shahnon, continue.
Okay. And then the last for this question 3B is write the thermochemical equation for combustion of xylose. I think this one is very, very easy for you. C5H10O5. C5H10O5. So where is, okay, here. First, C5H10O5. This is xylose. We already know this is xylose must be solid. Okay, xylose, because this is sugar. Sugar must be in solid form. And then oxygen here. Combustion need oxygen. Okay, just put it like that. And then the product is carbon dioxide in gas form, and also H2O in liquid form. And then we have to um, balance this equation. C here we have a 5, C here is 1, so just put 5 here, and we try to balance hydrogen. Hydrogen here is 10, hydrogen is 2, just put 5 here, and then oxygen. Oxygen here, 5 times 2, 10, 10 plus 5, 15. Here we have 5 already, 5 already, so make sure this become 10. So just put it 5, 5 times 2, 10 plus 5, 15. Okay, settle already. 1 mark. Usually for balance equation, only 1 mark. Okay, because very easy. Okay, and then for thermochemistry, construct a bond Haber cycle calcium fluoride in the solid state by using data below. Calculate the lattice energy for calcium fluoride. And this is data given: first ionization energy, second ionization energy, enthalpy of atomization of calcium, bond energy of fluorine here. Okay, we are given bond energy. Usually we will given the enthalpy of atomization of fluorine, but this one is bond energy of fluorine. And then electron affinity of fluorine, enthalpy of formation of calcium fluoride. Okay, and then we have to construct the bond Haber cycle. And to construct it, actually easy for you if you remember this formula. Okay, the formula is very easy. Phi L F equal to AAIEL. Phi L F stand for enthalpy of formation is atomization. Ionization energy is for electron affinity, and this is lattice energy. Phi L. Okay, if you can remember this, easy for you to uh, calculate the or construct a bond Haber cycle, and lastly calculate the whatever what we have to calculate in this one. In this case, we have to calculate what? Lattice energy. Okay, this one we have to calculate lattice energy. First, if you look at this question, F. Okay, we write the enthalpy of formation first. Okay, enthalpy of formation is, okay, this one is calcium fluoride here. Okay, this one is calcium fluoride, solid. Remember that it's come from its constituent. So here is calcium in solid form, and fluorine F2. Okay, in standard state, fluorine in atom in gas state. Okay, calcium solid and F2 solid. Now this is already balanced, this equation. And here is delta H for formation, negative 1220 kJ, right? Okay, after we finish the F, now we go to the A, atomization. Here we have atomization of calcium. So calcium here in gas state, and also for fluorine here must be in atom, all right, in gas state, but this one is 2, so we have to balance, we put it 2 here. Okay, and atomization of calcium is given below, positive 178 kilojoule. And atomization of fluorine not given, but we are given bond energy. Bond energy is positive 158 kilojoule. Okay, and for bond energy, look at here, FF bond. So this here is FF bond. That's mean, and actually the bond energy actually is double of atomization of fluorine. So this one we don't have to do anything, just put it plus 158. Okay. After that, we go to the ionization energy, but this one we have two ionization energy here. Okay, this is the first one, Ca plus gas, and then Ca2 plus gas, right? Make it here. And the first ionization energy is positive 590. And for the second ionization energy, 1150 kJ. And then electron affinity of fluorine, we just make it like this, F minus, okay, guess. And here we have a 2 mole, because here is we have a 2 mole of fluorine. So for the electron affinity, we have to time with 2 also here. So electron affinity of fluorine should be 2 times negative 328 kilojoule. And then the last one is lattice energy. Okay, this one is lattice energy. Okay, we already construct the bond Haber cycle. Remember that when we calculate the bond Haber cycle, don't forget to add the value with kj. All must be in kj, 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 and so on. Okay, and then to calculate the lattice energy, just follow the phi L here. Phi L. Okay, we have a phi L here. So the F is enthalpy of formation. So here is delta HF and so on. Okay. And then if I just want to this. Okay, the enthalpy of formation is positive, where is negative 1220. This one, negative 1220 kilojoule equal to, and then is atomization positive 178 plus, we just follow this rule. Then A here is positive 158, and then ionization energy. I know I is ionization energy. Yes, positive 510, positive 509, positive 590. Okay, and then second ionization energy plus positive 1150, and then plus for uh, electron affinity 2 times negative through 3 to 8, and plus lattice energy. Okay, like this. Lattice. Okay, we just follow the file here. Okay, and for this is for your general knowledge, or for your information. In lattice energy, we will have three three enthalpy that is a negative. Number one is enthalpy of formation. Number two is lattice energy, and number three is electron affinity. Only these three in negative. So our answer, the delta H lattice, must be in negative. If you do it wrongly, maybe you will get it positive, right? And if you calculate it, the answer is negative 2.640 kilojoule per mole. Okay, make sure that your answer must be in negative, because lattice energy cannot be positive. Lattice energy must be in negative. Okay, in Born-Haber cycle, only three that is negative. As I said, enthalpy of formation. Number two is lattice energy, and number three is electron affinity. The first electron affinity, because the second electron affinity will be in positive. Okay. All right. Okay. Okay, we'll settle this. And then B, what you expect the lattice energy of calcium chloride compared to that of calcium fluoride. Okay. The answer is what would be which one would be the higher in terms of lattice energy? And the answer is calcium fluoride. Okay, this is the answer. Lattice energy of calcium fluoride is higher than calcium chloride. Okay, this is the answer. Usually, this will be 1 mark. Okay, why? Okay, because explain. Okay, we have to explain our answer, and this is because the F minus ion here has smaller, okay, ionic radius than chloride ion. Okay, because actually in lattice energy it's depend on the ionic radius. Okay, um, the smaller the ionic radius, the stronger the lattice energy. Okay, because we know that fluorine in period 2, whereas chlorine in period 3, of course, element in period 2 smaller than element in period 3. Okay, so F minus ion, smaller ionic radius, and therefore the lattice energy of calcium fluoride is higher compared to the lattice energy of calcium chloride. Okay, thermochemistry. We already finished the thermochemistry. Yeah. Okay. Now we go to the question number 5. Question number 5 is electrochemistry. Okay, electrochemistry. In an electrolysis, a current of 0.25 ampere flowed through an aqueous solution copper to sulfate for 3 hours, 3.00 hours. Calculate the quantity of charge required and then calculate the volume of oxygen collected if the electrolysis was carried out at STP. Question number 1, very easy. Okay, I think this is first Faraday's law, Q equal to IT. All right, I is here 0.25, 0.25, T time must be in second. So 3 hours here times 60 times 60. And the answer is 2700 coulomb. Okay, 2000 coulomb. Maybe you will get, I think, 2 mark here. Okay, this one. And for the final answer, I think maybe two mark for this question. Very easy. Okay. Question number 2. Question number 2. Calculate the volume of O2. If we are given oxygen here, this is actually the clue for us that this is happen. This reaction happen at the anode. Okay, that at anode, and what happened? Oxidation of water. Okay, must be oxidation of water. I believe that, and I believe that 99.99%. If we have oxygen here, 99.99% oxidation of water at anode. I believe, even though here we have a copper sulfate here. All right, wow, copper sulfate, because a sulfate ion here, sulfate ion, SO4 to minus, and H2O here, they will compete each other to be oxidized at anode. And as we can see that we have oxygen here, of course, water will be the winner in this competition. All right. Okay. We have to know that. Oxygen, that's mean oxidation of water at anode. Okay. If we have let's say we have hydrogen, 90% if hydrogen reduction of water at cathode. Okay, reduction of water. But this one is oxygen, right? So we have to know how to write the oxidation of water. Okay, I show you. So 2H2O liquid. Okay, this is water. And then because oxidation, remember that oxidation, it will release oxygen gas, as mentioned here, oxygen gas collected. And don't forget the electron. The electron must be on the right hand side. Okay. Here the oxygen is 2 already. 2 already. Now we have a 4H, and for 4H we have 4H plus, and to balance this 4H plus is 4E. Okay, this is equation for the oxidation of water. Okay, oxidation of water. This is the reaction that you have to memorize it. Okay, and know how to write. Okay, and then this is very important. We know that 4E and 1 mole of oxygen. This means 4E here equivalent to 4 Faraday. Okay, equivalent to 4 times 96500 coulomb, equal to equivalent to, not equal to, equivalent to 1 mole of oxygen. This is very, very important. And now we know this one and this one, and then this one, 2700. All right. So we can calculate the mole of, now we can calculate how many mole of oxygen will be released at anode. Okay. So I just put it here, 2700 coulomb. Okay, jadi 2700 times 1 divided by 496,500 coulomb. And the answer is 0.00699 mole of oxygen will be released at anode when we are using 0.25 ampere at 3 hours. Wow. Okay. Okay. Now we already know the mole of oxygen. And then calculate the volume. Now, from number of mole of oxygen, we have to change it to volume at STP. Okay, at STP. And to do that, you have to look at your papers. Usually in the lampiran there, we can for STP. For STP, 1 mole of gas will occupy 22.4 liter of gas. So we can use it volume oxygen at STP equal to 0.00966 times 22.4 liter. So the answer is 0.1566 liter, right? After 3 hours of electrolysis, only 0.156 liter of oxygen will be released at anode, right? At STP. Okay. Okay, settle question number 5. And now we will go to the last question. Okay, this is the question. Only 6 question. Okay, for electrochemistry, also 2 question. The question is, a half cell containing 0.01 molar cobalt ion and a cobalt electrolyte is coupled with another half cell containing 0.1 molar AU3 plus aurum ion and a gold electrode using a salt bridge at 25 degrees Celsius. The standard reduction potential for CO2 plus and AU3 plus are negative 0.28 volt and positive 150 volt respectively. State the function of salt bridge. Okay. Salt bridge. You have to memorize this one. Function of salt bridge is to what? To complete. Number 1 is to complete the electrical circuit. Okay. the electrical circuit and maintain electrical neutrality in electrolyte Okay, this is the function of salt bridge. Okay, two. Number one is to complete the electrical circuit, and number two to maintain the electrical neutrality in electrolyte. Okay. Question number one. Question number two, write the cell notation for the above cell. Okay. To write the cell notation, first of all, we have to know which one will be, which one will oxidize, which one will reduce. Okay, we have to know that before we write the cell notation. Okay, if you look at this one, we have to use this one, what we call it, a more positive. I always use this one, more positive red cat. More positive red cat. This one very easy for us to remember it. More positive red cat means the more positive of standard reductive potential, it will be reduced at cathode. Reduction at red cat means reduction at cathode. So it is clear that which one? This one, AU3 plus positive, right? Positive 165. AU3 plus. That means AU3 plus will be reduced at cathode, and CO2 plus, okay, cobalt will be oxidized. And to write the cell notation, there is a rule. The rule is the oxidation we have to write at our left hand side. Okay, that means cobalt lah. Cobalt. So cobalt, cobalt, where is my, okay, wait a minute. Okay, it's cobalt in solid form, in solid form, because now I'm writing the electrode. Okay, when we try to write the cell notation, actually we write the electrode, and then the electrolyte, salt bridge, electrolyte and electrode. Okay, CO solid, this is electrode, and then the electrolyte slash here, and CO2 plus. Okay, this one CO2 plus, and because we have a molarity here, that's mean we have to put it, and this one is in aqueous form, and don't forget to write the 0.01 molar of CO2 plus ion. Okay, and if you look at this one is oxidation. CO, the number, the oxidation number is 0, and CO2 plus is positive 2, just from 0 to positive 2. And then we have a salt bridge, double slash, and then AU3 plus, okay, aqueous, don't forget to put 0.1, okay, 0.1 for 0.1 molar, and then slash AU solid. All right, this is this is what we call cell notation. Okay, cell notation for this equation. Okay, question number 3. Question number 3. Calculate the cell potential under the standard condition. Okay, calculate the cell potential under standard condition. First, before we calculate the cell potential, we have to know the E naught cell. Okay, E naught cell first, and then also we have to know the Q, because let me use this part. Okay, here. To answer this question, okay, E cell, we want to calculate the E cell equal to E naught cell, okay, minus 0.0592 divided by n log Q. This is general equation for this to answer this question. And we still don't know the E naught cell, and we also don't know the Q, the value of Q. So first, we calculate the, let me highlight this one first. Oh, sorry. Okay, this one and also this one. We try to find this one first, and then we just can put it here and we can answer the question. E cell, E naught cell equal to E naught cathode minus E naught anode. This is the, you have to remember this one. I think all of you already know this one. E naught, E naught cell equal to E naught cathode. E naught cathode, we already know here, cathode is aurum here, okay? Okay, this one, more positive, okay? Okay, positive 150, okay? Positive 150, okay? Positive 1.50 volt minus and negative 0.28, negative 0.28. And the answer is positive 1.78 volt. Okay, this is E naught. And then Q. What is Q? Q actually is, before we know the Q, we have to know the overall equation. We have to know the overall equation. How to the overall equation? Okay, look at this. Copper here, oxidation. Okay, CO, copper, cobalt, not copper, cobalt, CO. Jadi CO, all right. This is at anode. This is at anode. CO solid. Okay. And then CO2 plus 2E. Okay. This is half equation at anode. Okay. Oxidation. Right. And at cathode, this is what happened at cathode. Look at here. AU3 plus. Okay. From AU3 plus. AU3 plus. AU3 plus. Of course, plus 3E. Okay, because it's 3 plus 3E, then it's will cancel each other. The charge here is will become AU solid like this. Okay, this is half equation. And then we want to get the overall equation. Here we have 2 here. Here 3. So here we have to time with 3. 3 it's become 6E. Here times 2 it's become 6. Become 2. So the overall equation 3CO solid plus 2AU3 plus equals 3CO2 plus 2 plus equals plus 2AU solid. All right. This is overall equation. And then from overall equation, then we can use the Q. What is Q? Q is product. Here we have a product here. The product is CO2 plus. Okay, the concentration of CO2 plus times 3. And here we have solid. Aurum solid is not. We will not put it in the Q because the solid we cannot calculate the concentration. Okay, so only CO2 plus, and then divided by reactant. The reactant, we have a 3CO solid here, not included in Q expression, only aurum here, AU3 plus squared. All right. Now we can, oops, where is it? Okay. Now we can complete our E cell here. Okay, E cell. We already got all the information that needed to fulfill this equation. So the E cell equal to E naught cell, positive 1.78 volt minus 0.0592 N. What is N? N is here, 6E. Okay, 6E. 6E. That means N equal to 6. N equal to 6. And log Q. What is log Q? Concentration of CO2 plus to the power of 3 divided by AU3 plus to the power of 2. Okay. Nah, positive 178 volt minus 0.0592 divided by 6 log and CO3 plus our CO2 plus 0.01. Okay. 0.01, 0.01 to the power of 3, and for AU3 plus 0.1 to the power of 2. Okay, and the answer should be positive. Don't forget to put positive, 1.82 volt. This is E cell for this equation. All right, I think I already finished our discussion. Okay, 3 topics, each topic 2 questions, and I think if you can follow my my lecture, okay, I think you can answer this question very well. So any question from the student? Any question?
So far, no question.
Oh, so far no question. Good. All right. So if no question, oh, we already more than 4:30. So go back to our moderator.
Okay. Thank you, Cikgu Shahnon. So I give you the last passcode, number 6. Last passcode is number 6. So with God's grace, we are done with today's session. We have learned a lot from Cikgu Shahnon about physical chemistry, revisions. So congratulations to those who are able to follow our sessions from the beginning till the end. And thank you very much, Cikgu Shahnon, for such an interesting lesson. Please check the chat box for the certificate link, and please off the live chat button and click subscribe button if you haven't. This is to show your appreciation to Cikgu Shahnon for giving you a free lesson today. Don't forget to click the bell button too, so you won't miss out any new videos and live classes from Cikgu Shahnon. If you like today's class, then please click like and share it to your social media friends. Let's share the knowledge you received today with them. Sharing is caring, right? Once again, I would like to thank Cikgu Shahnon for the interesting lesson. Thank you also to Teacher Kong and Teacher Tang for being with us today. I think that's all for now. See you in another session. Goodbye everyone. Have a nice weekend.
Bye-bye.
Berita baik untuk semua. Kini Akademi YouTuber memperkenalkan sistem mata ganjaran kredit AYU untuk dikumpul. Jom ikuti kelas tuition live AYU untuk mengumpul kredit AYU dan berpeluang menebus hadiah-hadiah yang menarik. Hadiah bernilai lebih RM10,000 disediakan secara percuma untuk pelajar seluruh Malaysia. Apa tunggu lagi? Tebus ganjaran hebat ini sekarang. Layari www.academyyoutuber.com untuk maklumat lanjut.